Hello, this is Brad here, and today what I'm going to be doing is just highlighting an interesting thing that I encountered in the Mass software. At first, I saw it and thought that it might be a bug, but actually, it's just highlighting that something that's very interesting. So I've got just a pretty ordinary looking design here. You'll see that I've just turned some things off just for the sake of demonstrating this example. And if I show you quickly the loads that I have on this structure, you'll see that I have some wind loads. I didn't apply any seismic just because I'm not really getting into the different seismic properties or things like that. I just wanted to get a quick design. I applied some axial loads, dead, live, and snow that you see here. But the interesting part of this design, I'll quickly go back to what I have here and show you that all of these are currently assigned to Group A. If I click on the Assign Groups tab, you'll see they're all using the same cross-section. Everything about these designs is the same. However, when I look at my interaction diagram, look at what happens. I've got 4 different curves. And like I said, I saw this at first and thought, something must be wrong. And so actually nothing is wrong here. The software is doing exactly what it's supposed to be doing. But we are seeing 4 different envelope curves, one for each part of the shear wall. So looking here, you can see on the left, I've got this diagram of my shear wall. And you'll notice that I have flanges here as well. On the bottom here, I've sort of overlaid my main multi-story tab with the individual elements. But if you look at those different elements, what you'll see is that they're exactly the same. I mean, that's where all of the different analysis goes. But I checked each one of these thinking that maybe something was wrong there. Maybe there were differences between these as to where those 4 different envelope curves were coming from. After all, each one of these is generating its own interaction diagram and then sending it to the main multi-story one. So I thought maybe there was a bug, something going on there. But I just want to specify, I did go through and check it, and all of the cross sections were exactly the same. Same F per mem values, same bar placement, same grout. And so it wasn't that. Actually, the reason for this, I'm going to give just a little bit of background here, referring to our design standard, the CSA S304 2014 edition. It's the same as in the 2004 for this clause that I'm talking about. In 7.6.1, it's referred to from the reinforced section as well. But basically, when it comes to flanges, there's only a certain section that we can consider. So we're talking about specifically the overhanging width of a flange that we're talking about. And so there are 4 different things that we need to consider when we're calculating this. The first one is just the actual size of the flange itself. But looking at part A, that's actually the same for each story that we're looking at. And so that wouldn't explain any differences that are coming up there. Moving on to point B, looking at half the distance to the next web. I mean, this is something that would need to be considered before actually modeling this into the Mass software. But once again, it's going to be the same for each story. It's more a function of your building's layout. Looking at the requirement C, 6 times that flange thickness, that is something, once again, that's going to be the same all the way up and down the height of our structure, so that's not going to explain it. But then we get these different requirements in part D. There's two different ones here, basically talking about the distance from the top of our shear wall. So when we're looking at the critical section, we're designing a shear wall element. We are choosing the location, we're designing it for moment for shear, and then whatever that distance is, we are either dividing it by 12 or by 16, depending on whether or not we have a symmetric shear wall design. This is actually something that is not the same for each story, so this is where I thought I would look first when it comes to getting to the bottom of this. So let's just take a look again at our shear wall. I'm going to zoom in real quick to explain just the terminology. I'm referring to flanges. So on the right side, I'm just looking at that part of the flange. That's actually flange number 1. We don't number them left to right. We start at the compression end of our wall, just in the analysis engine and everything. And then if we look to the left, that's flange number 2, and we have the tension side. You'll see that part of that flange lines up with the web, and so I've actually got it labeled on both sides. It's 190 millimeters, so 20 centimeter unit, and so we're dealing with specifically what the overhanging distance is. So actually in both directions, so on the right flange we have LF1 and LF2. This is basically the distance that we can consider that effective flange to be overhanging, and then we have F3 and F4 on the left flange that you see there as well. So if we look at these, we can actually look in the individual shear wall modules. This is under the detailed shear wall properties. And you'll see we actually get different values for each one, for story 4, for 3, for story 2, and story 1. And so that was something that really stuck out to me as a difference between these different designs. Looking then back at our cross section, let's compare how these different values are calculated to see where that difference comes from. So starting at story 4 at the very top, you'll see that it's only 3 meters, the section that we're designing at the base of that shear wall element, is 3 meters away from the top of the wall. And so if we plug in that 3,000 millimeters there, we get 250 millimeters. And so the way that we consider that in our design is looking at that LF1 and that LF2, those are each equal to 250 millimeters. So adding in the area of our flange that lines up with the web, we get a total of 690 millimeters at story 4. Moving downward to story 3, now this value is going to be bigger because now that distance from the critical section to the top of the web, we have an extra story above that, and so that value is now 6 meters. And so if we divide that by 12, we get 500 millimeters. So then looking at our LF1 and LF2, once again, you'll see instead of 250, now we have 500. And so you'll see we have more of that flange being effective now at 1,190 millimeters. Moving down again to story 2, I think you are going to notice a trend here. But now we're 9 meters away, so this value goes up to 750. And so as a result, we get an effective flange area of 1,690 millimeters. And then getting down to the very bottom, this actually worked out very nicely. I made this example, the geometry lined up like this. And so it worked out where, since we're 12 meters away at the very base of the wall from the top, if we look over here, we have exactly 1 meter for LF1 and LF2. And so we get a total of 2,190 millimeters, and look, that just happens to be equal to our entire flange in this case. So then if we go through, let's look back at our diagram. We have these different envelope curves that show up there. If I go back and instead of looking at the regular cross-section or the elevation that we're used to, we're looking at the flange. And so what I'm going to do here is highlight the area that intersects with the web. So that's what you see. Here's the shear wall web, and these are the flanges. And so now if I overlay from there those effective flange areas that we calculated, you'll see as we work our way down, we have more and more of our flange that's effective. So then translating this over to our design, you'll see, at this point, I think it makes more intuitive sense that at the very bottom of our wall, we're actually able to use the entire flange. And so that's where we get the larger envelope curve that shows up there. And then as we work our way down, you'll see we are able to use only less and less of that, working our way up the structure. And so by looking at it that way, you'll see this is where, even though we have the same cross-section, it's not really the same cross-section that we're looking at. Another way that you can look at this actually is, even though it is the same cross-section, you can think of it as basically cropping off those outer edges of each flange as we work our way up the wall. Usually if you look at these load combinations, so story 4 load combinations are down at the bottom, and they're sort of connected all the way out to story 1. So that's where we have more loads. And so that's where it's more critical that we're able to use more of our flange. In terms of actual practical design scenarios, this doesn't throw things too far off. But I just wanted to quickly explain, the software isn't doing anything wrong here. The reason why you're seeing multiple curves under the same group, it's not a bug. The software is doing what it's supposed to. It's just its way of taking into account how much the flange that we're actually able to use. If you have any other questions about things like this that come up, or if you find this interesting, please just let me know. It's something that I'm considering doing more of, and so please just feel free to reach out. You can contact us, Canada Masonry Design Center. Just Google us, give us a call, send us an email, and we are happy to help you with your design. Thank you.